So we're talking about covalent bonding, and we are modifying our diagram here like we had seen these for single atoms before, showing psi squared, which is proportional to the probability of finding electrons. And I've modified this here to show two hydrogen atoms. So here's one nucleus, here's the other, and it shows how there's a greater probability of finding the electrons between the two nuclei. And it's that mutual attraction of the two nuclei to the same electrons that forms the bond between the atoms, or that holds the atoms together. Now, as we'll find out later on in this chapter, those two electrons, that shared pair of electrons, is actually in a new orbital that's called a bonding orbital. But this holds the atoms together. So it's that simple. Essentially, the two atoms are fighting over the electrons, and they are stuck together because they're hanging on to it. It's like, say you're fighting with your little brother over the game controller, and neither of you will let go, so you are a unit until one of you gives in and lets go of the controller. Okay? So that's the same idea. Now, there's other ways we can look at bonds too. So let's look at it this way. Here's our two protons, and again we're focusing on H2 here, and here's the two electrons. Now, if we look at it like this, let's look at it from the perspective of effective nuclear charge. Now, if you've got just a single hydrogen atom with its lone electron, the effective nuclear charge right now, that this electron is experiencing the force of +1 from the nucleus in full, because there's no electrons to shield it, right? Now, there's still room for another electron in this shell. So if another electron was to wander along here, it could get stuck in this shell because it too would experience the force of attraction to that nucleus, because there's no electrons between it and the nucleus shielding it from that charge. Yes? Yeah. Yep. Now, you might have to kind of push it close enough to get within the shell. Now, if another atom comes along with its electron, here's what can happen. This new hydrogen atom that's coming along here, it can do this. It can kind of merge its outer shell. This is at least one way we could look at it. It can merge its shell, its 1s, with the other atom, like this. Now, in this way, one way you could look at it is that we could now say that they both feel like they have a 1s2 configuration, because they both kind of feel like they have a full outer shell now. And that's one way that this is often explained in covalent bonding, that atoms are going to bond in order to complete their outer shell through sharing. You don't have a complete outer shell, you got two options. You can steal somebody's electron, or you can share with somebody, because sharing kind of has the same effect. Right? If you don't have a coat and somebody else has a coat and it's cold outside, you got two options. You can either steal their coat, or you could share their coat. Right? And if you share their coat, you both feel like you have a coat. Might be a little more cramped, but that's the same idea here. Now, so we can see why this might happen, because this electron is going to experience attraction to that nucleus, and there's still room in the outer shell of this atom, and likewise for this atom. There's still room in the outer shell. Now, that's key. Now, why doesn't another atom come and join the party? Because now the shells are filled. So let's say here's another atom coming along, and it wants to join the party. Problem is, for this electron to get involved here, it can't get into that 1s subshell. It's full, right? So what would it have to do? It would have to go into the second energy level, but then the effective nuclear charge for that electron would be 0. So let's say, in other words, let's say another electron, picture this other electron coming in here and trying to get into that shell. It can't fit inside, so then you say, well, maybe it'll just start a new shell around here and then get in that shell. It's not going to do that because now there's 2 electrons between it and the nucleus. So it would actually be repelled. And we could do a similar model with more complex atoms. In fact, it works a little bit better for that with more complex atoms. So if in F2, for example, if we have a fluorine atom that's 1s2, 2s2, 2p5, and then we have another fluorine atom that's 1s2, 2s2, 2p5, when they're separate, if they can share one of these, now what would that look like? Let's draw it in terms of, let's draw it with the orbital filling diagrams. So this is what we have for one. Right? Now you could picture, so if this is one fluorine atom, we could picture another fluorine atom coming along and doing this sort of thing. So the red are the p orbitals that are being contributed by the atom on the right. And they can share. And you can see in this depiction also that now they both feel like they have a complete outer shell, that they are have a noble gas configuration. They're going to have a really strong hold on all those outer shell electrons. In other words, they're going to be stable. They're not going to want to give up these outer shell electrons because they're held by a high effective nuclear charge. And they're not going to want to accept any more electrons because this shell is full, and the only way they could add any more electrons would be to go into the 3s, and for the 3s electrons, they'd have an effective nuclear charge of 0. There would be an effective nuclear charge of 0 because there'd be all these electrons between the new electron and the nucleus. Another way to look at bonding. So this is kind of, we're just looking different perspectives at bonding. Here's one. Here's the second way of looking at it in terms of electron configurations. Third way of looking at it is in terms of potential energy. Now if we draw a picture of a graph of potential energy on the y-axis, and then over here we're going to put distance between the nuclei. If we have 2 hydrogen atoms, so out here I'm going to put the 2 hydrogen atoms are widely separated. When the 2 hydrogen atoms are widely separated, and then it's way out here, and then as we bring them in, what we're going to be doing is we're going to be pushing them together to the point where they're squished right into each other on the y-axis. So this is 0 distance between the nuclei. If we could put their nuclei right together, that would be right along the y-axis on this diagram. Now picture yourself doing that. There would be several forces that would come into play. As they approach, the first thing we would start to experience in terms of forces is a repulsive force between the electrons of the 2 atoms. And it would look something like this. So this would be repulsion, electron to electron. So the electron of one atom would start to repel the electron of the other atom. And as you tried to press them together, this repulsive force would get greater. And so the potential energy increases. Now what does this mean? If I take 2 magnets and I put them with like poles toward each other, so this, let me get some better magnets, hang on. So if I turn these so that they're repulsive, the closer that I put them together, because they're repelling, the greater the potential energy of the system. So that if I press them together, the system has lots of potential energy, and if I release it, well, actually these don't work that well. I'm holding them together again. This system has a high potential energy. How do I know? Because if I release it, that potential energy is converted into kinetic energy. So potential energy, kinetic energy. All right. So this system has a low potential energy right now. I can't even feel them pressing on each other. And if I let go, nothing happens. They don't move toward each other. But as I push them closer, the potential energy is going up. So these are the two hydrogen atoms. Their electrons start to repel, and I'm going up the curve as I go toward the left, like pushing a ball up a hill. And if I let go, then the ball rolls down the hill. They go away. They try to find the lowest potential energy, and that's what systems do in nature. They seek the lowest potential energy position. And actually, we would also have repulsion. If we could get them closer, we would start to see repulsion from the nuclei repelling each other. And that's why fusion is so difficult to initiate, because to get two nuclei to fuse together, you have to overcome that repulsive force. And as you get in really close, that becomes really strong. So this red line is repulsion from the protons repelling each other. But don't forget, we also have an attractive force acting in the opposite direction. This is electron to proton attraction. So in other words, we have the attraction of the electron of one atom to the proton of the other, to the nucleus of the other. And so what happens is this system seeks the lowest point on this curve, just like a ball would roll down the hill and find the lowest spot and stop. Okay? And so this point right here on this x-axis is the internuclear distance. In H2. They're just naturally going to find the distance that minimizes the potential energy of the system. They're going to seek that distance. And it's kind of cool because all of chemistry can be viewed as atoms simply seeking the lowest potential energy position that's currently available to them. The whole universe can be understood in that way. Your atoms that make your body would really like to be in a much lower potential energy position. Right? Like CO2, for example. And so we're always fighting that, right? And there's a lot of, we're trying to keep them from having access to those lower potential energy positions. All right, so that's just kind of some theoretical stuff about what a bond is. And it turns out that bonds are always pairs of electrons. They're always pairs. One pair is a single bond. Okay, you can have two pairs, of course. Two, and that's a double bond. And then we can have a triple, but you're not going to get a quadruple bond. Pair. Three pair. So you get single, double, triple, but they're always in pairs. Now we want to be able to draw diagrams of bonding arrangements in atoms, M in molecules. So that we can, because eventually we want to be able to say something about their geometry. We want to be able to predict their geometry. Why would I care about their geometry, their shape? Any ideas, Nick? Okay, so we might be able to predict how they react, how they behave. Anybody want to get specific? What are some specific things that shape could tell you? Yes. Polarity. So polarity can tell you what? What does polarity have to do with? So if I know it's polar, what can I predict? Okay, what can I predict about its behavior? Okay, whether it will have attractive intermolecular forces. This is where we're going with this. And those of you who hadn't had Chem A or IPS might not have seen it before, but we will. Intermolecular forces. So it has to do with whether two molecules will be attracted to each other. Now, what properties would that affect? If two molecules are more strongly attracted to each other, what might that affect? Anyone over here on the left? Let's say two molecules are really strongly attracted to each other. Why would I care about that? Okay, it might be harder to dissolve. What else? They're more cohesive. Yep, that's true. They're going to stick to things, to each other. Okay, surface tension. That's a good one. Nick? Purity? What do you mean by that? Okay, you might tend to get less likely to have contaminants in it. That's possible. How about boiling, for example, or evaporation? If you're evaporating something or you're boiling it, you're separating the molecules, right? So if we have a shape that makes the molecules more strongly attracted, we would expect a higher boiling point. And that's what we find. Something I was looking at today that I didn't know much about, there's two big theories of how smell works. And one of them is called the shape theory of smell, and it says that it's the shape of the molecule that has the most to do with smell because it literally fits into receptors in our nose that match with it and then signal a certain smell. The other theory is that it also has a lot to do with how the molecule vibrates, that it basically vibrates at the same frequency as the receptor site. And so it's got some kind of a quantum effect. So that's a more sophisticated view. But in both cases, the shape is important for the smell. So that's kind of cool. And dogs can smell like hundreds of thousands of times better than we can. So, okay. So that's why we want to do this. That's the purpose of doing this. So how do we draw a molecule? First of all, what is it going to look like? Here's your basic Lewis structure for methane, for example. Or you might have one that looks like this, which shows a double bond in there. And then we've got these dots over here. So this is what we're going to start to draw. And then the next step after we learn to draw these is we learn how to figure out what the shape will be, the geometry, the three-dimensional geometry. We're going to learn how to figure that out from this. Now, it's pretty simple how to do this. There are a series of steps that you should adhere to. And you have to follow these religiously. It's kind of like balancing redox equations. If you're not the type of person who likes to follow steps, and so you skip steps, then there's two things you're going to get wrong. One is balancing redox equations, and the other is drawing Lewis structures. All right? So you got to follow these steps. Step 1. You count up all the valence electrons. In the molecule. And then we have to add a little extra thing on here. We're going to add electrons for anions, because these might be polyatomic anions, in which case you have to add electrons or subtract for cations. All right? That's the first step. So we're going to take 3 examples, and we're going to carry these 3 examples right through the whole process. The first is OCl minus, also known as ClO minus. And we have CH3OH and SO3 2 minus. So we have the hypochlorite ion, the sulfite ion, and methanol. So the first step is we count up the total valence electrons. It's going to be, in this case, 6 for the oxygen and 7 for the chlorine, plus 1 for this negative charge right here. So the 6 is from the oxygen, the 7 is from the chlorine. You know the quick way to figure out valence electrons? If this is a periodic table, this is the p block. Group 13, group 14, group 15, group 16, group 17, group 18, and the valence electrons is 3, 4, 5, 6, 7, 8. And because when we're doing covalent bonding, we're always dealing with nonmetals, that's all we need to know, except that hydrogen has 1. Hydrogen has 1 valence electron. So this is going to be 14. Yes? They are not going to be involved in covalent bonding, but they would have 1 and 2 valence electrons. Right. Okay, so for methanol then, I've got 1 carbon, that's 4 electrons. I have 4 hydrogens, so 4 times 1, that's for my hydrogen. And then I have an oxygen with 6. So that's the carbon, it's the hydrogen, this is the oxygen, which adds up to 14 again. These are just the valence electrons because it's only the valence electrons that are involved in bonding. They're the outer shell, they're the ones getting involved. Now I've got oxygen and sulfur, so I've got 6 plus 3 times 6. They both have the same number of valence electrons. They're in the same column, group 16, plus 2 for these extra 2. So when that charge that's right there on the polyatomic ion, that is telling you how many extra electrons there are in that molecule. And so we have to tack that on. So we have 26 here, right? Okay, that's pretty simple so far. And this really is pretty simple if you stick to the rules. Stick to the steps. Number 2, draw a skeleton structure using single bonds. And so that'll look like that for the first one, ClO. For the second one, we'll have this. And for the third one, now this is deceptively simple in terms of the way it was stated. There are other ways you could draw these. So you have to use some rules of thumb here. Rules of thumb. Carbon usually forms 4 bonds. Oxygen usually forms 2 bonds. And hydrogen always, almost always, forms 1 bond. So that is a good rule of thumb. But there's another one we need here too. So first is we have a few rules about how many bonds are usually formed. Now, why is this going to help you to draw the skeleton structure? For one thing, you're never going to put hydrogen in the middle of a structure with multiple bonds coming off. So that's what I'm saying here. You use these rules to help you figure out how to arrange the atoms. And the last one is symmetry. Actually, this isn't the last one. Nature loves symmetry. So, for example, when I draw this SO3, I don't put an O in the middle and then the S sticking off one side. I go for the more symmetrical structure. Okay, so this is how it's going to guide you. These are the principles that are going to guide you in drawing these. Fifth is, I knew there was a fifth one. Symmetry. Atoms with the most bonds go in the center. Oh, this kind of wheel shape. So it's related to that. In other words, don't draw this one like this one right here. I'm not going to draw this like this. This sort of molecule that's a circle or a square or a triangle is not very common. It can happen, it's just not real common. So don't do that as your first approach. Most of the molecules we'll be drawing will have a central atom with others sticking off of it like the spokes of a wheel. So when I say wheel shape, I mean like this. It's not really wheel shape, but spokes of a wheel. So anyway, use these rules of thumb. And so there you go. We have our skeleton structures. Step 3. Stop me if you have questions. Deduct 2 electrons for each single bond in the skeleton. Deduct 2 electrons for each single bond in the skeleton. So for the CLO ion, what we're going to do, we started off with 14. I had 1 bond in my skeleton. So I'm just going to subtract 2. Because the bond is a pair of electrons. So in other words, you've already used your 2 of your valence electrons to make that bond between the atoms. You've used up 2. So you take 2 away. So we're doing like a little accounting process here. And that leaves us with 12 electrons. For the methanol, we started with 14, but this time we used a lot more. We used 2, 4, 6, 8, 10 electrons just to make the bonds. So just to make the bonds we used 10, which leaves us with 4. 4 that we still have to work with. The last one is SO3 2-. This one started with 26. We used 6. So we made 3 bonds, and so we're left with 20 electrons. So that's a pretty simple step. Although I say it's pretty simple, but you'd be surprised how many times people will make simple subtraction errors at this step and so get the wrong answer. So be careful of that. If you need to, use your calculator so that you don't. It should not be a pride thing, like I'm not going to use my calculator because this is a simple subtraction. Yeah. It should not be a pride thing is what I'm saying. Okay, so distribute. Distribute these remaining electrons. The The ones that are in the bonds have already been spoken for. So we're going to distribute the remaining electrons to give each atom a noble gas structure, which is an octet. Have you heard that word before? Octet? That is 8 electrons in its outermost shell. That's the octet. And remember, that's as many electrons as you're going to get in the outermost shell, well, usually, without opening up a new shell. So this is to give each atom an octet, except for hydrogen, of course. Which only needs 2. So here's what we do. For the first one, we've got Cl and O. We've used up 2. We have 12 remaining. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Done. Everybody's happy. We have 8 around the chlorine because the line, the bond counts as 2. So it goes 2, 4, 6, 8. And we also have 8 around the oxygen. 2, 4, 6, 8. So everyone is happy. And we're going to put a bracket around this, and we're going to put a negative charge, just to remind us that the whole thing has a negative charge. Which one of these is the extra electron? Who knows? But if you counted up all the electrons and protons in this thing, you'd find out you had 1 more electron than protons. And one of them, that extra one, is somewhere in these valence electrons. There's a hand up. Now notice, this is different. When we do this, we don't care who originally owned the electrons. We don't care. Atoms are communists. Basically, when they're going to get together, everybody throws all their electrons into a common pool, and then they redistribute them according to the need of each. From each according to his valence electron number, and to each according to his need. That is the dictum of the atom. So what does the next one look like? Well, in this one we can see that the carbons are already quite satisfied because they're surrounded by 8 electrons. Each of them has an octet. 2, 4, 6, 8. Remember, the bond counts toward the octet. And fortunately I have 4 left because oxygen needs 4 more. Now, by the way, when you distribute them in pairs. Distribute them in pairs. So now this one's happy. Lastly, we have the sulfite ion. We had 20 electrons remaining, so let's start distributing these. It takes 6 for every oxygen to fill up the octet of every oxygen, and then it takes 2 to fill up the sulfur. Put a bracket around that, put a 2- charge on there. Okay? Simple as that. Now, these are all pretty simple cases, though, so it gets a little bit more complicated. Step 5. If too few electrons, if you don't have enough electrons, you form multiple bonds. So we're going to have to introduce another example here. So step 5 is if you run out of electrons. So let's see what that would look like. Nitrate. If we go through the steps for nitrate, we're going to count up the valence electrons. We got 5 plus 3 times 6 plus 1. That is 24, right? So I've got 24 valence electrons. The next step is to draw my skeleton structure. Now I'm going to take 24 minus 6. This is the next step, and that leaves me with 18. So why did I say 24 minus 6? 3 bonds, right? 3 bonds and 2 electrons in each. So I've got 18, but what happens when I try to fill everybody up? Well, I can take care of the oxygens, but I can't take care of nitrogen. I don't have enough. So if you don't have enough, you make a double bond and you go back to step 2 or step 3. So you make a double bond. So I made a double bond, and now I go back to the step where we do the subtraction. Which one is that? 3. Yes, it could be on any of the oxygens. In this case, those oxygens are all equivalent. So they're all nitrogen to oxygen bonds, so it doesn't matter which one. In reality, that bond is actually kind of shared across the whole molecule. But we can draw it on any one of them. So now I've got 24 minus 8, which leaves me with 16. And you might think, oh, well, now it's even worse. Now I have even fewer electrons, but watch. 6, 12, 16. So now it works. Making the double bond, it saves electrons, it conserves them, because electrons that are in a bond are double counted. They're counted towards the octets of 2 atoms. Yeah, Jojo. Yep, the whole thing has a charge of -1. It's in there somewhere. It's one of those. It did when we added it in at the beginning. Yeah. This is where we took account of that extra electron. We threw it in the pool. And then we used it to distribute amongst everybody, but we don't really care where it ended up. We don't know. All right, so that is the first kind of problem that we might see in N2. We find out that we've got 10 valence electrons, and so we end up having to make a triple bond in order to satisfy everybody with only 10 electrons. Step 6, too many electrons. So you can have this problem too. There's too many electrons. Let's look at xenon tetrafluoride, one of the rare molecules that's made with a noble gas. So we have xenon tetrafluoride. By the way, fluorine can fight with a noble gas, but there aren't many atoms that can do that can bond with the noble gas. So xenon tetrafluoride has 36 valence electrons. But when I make the molecule, I'm only going to be subtracting 8. So 36 minus 8, 28. I can see I got a problem because xenon is already full. It's already got an octet. It's only going to take 24 to fill up the fluorines because they each only need 6. I've got 4 extra electrons to do something with. What do? You put them around the central atom in pairs. You basically just have to stow them somewhere, so you're going to put them in the middle. Put them in pairs around the central atom. This is called an expanded octet. And the way that they interpret this is they say that the D sublevel, just inside the outer shell, part of it gets sucked into the outer shell and basically gives the outer shell a greater capacity. Yes? Yes. Yeah, so in these you could get SF6, for example, sulfur hexafluoride, when those extra electrons are actually more bonds. So now we could have 6 bonds. Or 5. Yeah. So that's when you have too many electrons. Yep. Put them on the central atom as pairs, as unshared pairs. By the way, these are called unshared pairs. Unshared pairs and bonds. Those are the 2 types of electron pairs, unshared pairs and bonds. Unpaired shares. Number 7. A few weird exceptions. I always misspell weird, sorry. Oh. A few weird exceptions, or a couple to be exact. Beryllium Difluoride, which I wouldn't even think that would be a molecule. I would think it would be an ionic compound because beryllium's a metal. So that's weird to begin with. And then boron trifluoride. Now these are molecules that you should just memorize, because if you do the Lewis structures for these, you will not get this answer. So those are some weird exceptions. Boron trifluoride, beryllium difluoride. Let's see. One more thing I wanted to talk about. What if you had an odd number of valence electrons? Well, we know, I mean, right off the bat, if you see an odd number of valence electrons, you know you have a problem. So NO, if I want to do nitrogen oxide, I'm going to say 5 plus 6 is 11. And I know I've got issues. It's going to end up looking like this, with an unpaired electron down here. And what's going to happen is this is going to be a highly reactive molecule. This is going to be a highly reactive molecule called a radical, or a free radical. It's a free radical. And so it's highly reactive, and they're not very nice to have floating around your bloodstream and stuff like that. And there's other nitrogen compounds like this. And you would see this, if you were doing a Lewis structure, this would just happen, because you'd end up with that one leftover electron. You just have to pop it on an atom somewhere, and you would know that it wouldn't have an octet. So it's electron deficient. Electron deficient. Yes? You're going to fill up the atom that is more highly electronegative. And because the oxygen is a little more electronegative, it's going to take that, make sure its octet is full. Right? If anyone's going to go without, it's not going to be the strongest one. Okay, questions on those? Let's try one, shall we? We got a few minutes. Let's do try SO2.